Hello and welcome back. It's past midnight here. I'm a bit tired, but I thought that I would try recording this video day of. This is 2023, day 4. Let's get into it. A lot of flavor text. Let's look at the input first. So basically you get a row of numbers and separated by this bar in the middle. These card IDs are not relevant for either part of the problem, so we can discard those. Basically, each line represents a scratch card. And the first category of numbers before this pipe separator, these are winning numbers. And then these numbers after the pipe separator are numbers that you have on the card. And for part 1, the question essentially asks, first of all, for each line, how many of the numbers that you have are in the winning numbers? And then having found those amounts of winners, let's call them, for each line, you apply a scoring function. And if you have one match, then you get 1 point. If you have no matches, you get no points. And then every successive point after that doubles your point count. So let's see. Card number, so you have four winners in the first line. So you get 1 point for having 1, 2 points for having 2, 4 for having 3, and then 8 for having 4. Okay, fair enough. Let's solve this one first before going into part 2, and we'll get into all the parsing of the lines and all that. Once again, back in APL. So let's see. I have the test input, I think. Yep. And so for each one of these, we can, first of all, I think that it makes sense to split on both the colon here and the pipe. And we can split on multiple characters by using membership. So we can say omega in either colon or pipe. And that gives us a Boolean vector, and we want to not that, so we get the characters that are not either colon or pipes. And then we can partition, and that splits everything up. We can discard the card numbers, because those aren't relevant to the problem. And then for each one of these, we can execute to turn them from strings into numbers. And then we can reverse, so basically swap the positions of our two groups here. And then we can find occurrences of the first group in the second group by doing a membership reduce. We can break that out of a box, and then we can add all of them up to get basically our counts of winners for each one of our lines. So we'll assign this to C for counts. How about that? Okay, so that's the count of winners for each line. And then, so the scoring function essentially doubles on every subsequent point. And so we can probably use exponentiation of 2. So like 2 to the, 2 to the second power, 2 to the third power, etc. 2 to the 0th power is worth 1. And our problem description says that if you have one winner, it should be worth 1 point. 2 to the first power is 2, and our problem description says that if you have 2 winners, then you should get 2 points. So basically, we should subtract 1 from our counts here, and then we can do 2 exponents. And you'll notice that on lines where we don't have any winners, we end up getting a -1 when we subtract 1. Excuse me. We end up getting a -1 when we subtract 1. And so 2 to the -1 is 0.5. We can turn these into zeros by flooring, and then we just add all of them together. So we're just sort of shifting our counts a little bit, exponentiating 2, essentially, to take care of all of the doubling. And then, yeah, we just floor to take care of the case where there are no winners in the line. So we get 13, and for part 1, that is indeed the answer for the test input. Now, part 2 is very interesting. Okay, so this says each time that you, so starting from the first card that you have, so starting from the first line in our input, the number of winners is, you get copies of the following cards based on the number of winners. So in our case, line 1 had 4 winners. So we would get a copy of card 2, a copy of card 3, a copy of card 4, and a copy of card 5. So we get 4 copies of all of the subsequent cards, right? And then you keep going and you go down to card 2 and you say, okay, counting the original card that you started with, as well as any copies that you got from card 1, how many winners are on all of those cards? And then based on how many winners there are there, again, you'll get copies of subsequent cards, right? So you can see in the example, like card 1 has 4 matching numbers, so you get copies of these cards. Then you have 2 copies of card 2, so you get a copy of 3 and 4 on the original, and you also get copies from the copies, et cetera, et cetera, et cetera. So the way you might solve this in an imperative language is you probably do like a double for loop or something like that, where you iterate over all of the cards, and you also you have an inner for loop that iterates over maybe like an array or a dictionary, and you're constantly updating the count of the cards there. That would be difficult to do in APL, so we are going to take a slightly different approach. So we already have all of our counts. These basically say how many winners are in each exist for each card, and essentially the plan is going to be, you can think of it almost as sort of like transforming it into a graph problem or something like that. Basically, we're going to construct a matrix where for each row, we explicitly lay out the cards that are supposed to be added, and then we can use matrix multiplication in order to find the total of all of the cards once we sort of iteratively add all the winners. It'll make more sense in a minute. Just hang with me for a sec. So the first thing we want to do is build that matrix, and we can do that first of all by taking, if we look at the length of C, we can see that it's 6 elements long, and then we can get the range of indices for each of the elements in C by doing iota here. And then with C, we're going to run a function on each of the pairs from C and its index, right? And we're going to add them together, and then we're going to take the index and we're going to concatenate it. So this, you can sort of think of it as, well, and we're also going to add 1. So remember that we're 1 indexed here, but let's take a look at C and look at what we've just constructed. So for the first element in C, it says that we get 4 more cards. And what we've done with this function up here is we've sort of constructed ranges for each one of these. So we can say, okay, from cards 2 inclusive to 6 not inclusive, we get an extra card for each one of those. So we get an extra second card, third card, fourth card, and fifth card, but not a 6th card. right? For our second card, we can see that C is 2 at that index. And so again, we have a range from the following cards, the third and the fourth, but not the fifth. Again, for 4 and 6, 5 and 6, and then for these ones where there's no winners, because the top of the sequence is exclusive, these just end up not adding any other cards. So basically, we're constructing ranges here for the indices of the cards that are supposed to be added. And we can put this into a matrix by using interval index, let's assign this. So we're assigning it to I for indices. These are just the vector of indices in C, right? Okay, interval index. Let's see if I can find it. So basically, given a sorted left argument, interval index will find the index that it sort of slots into for every element on the right. In Python, I think this is, it's been a while. There's some sort of like binary search or like bin search or something like that that does something very similar. Basically, what it's doing is it does a binary search on the left argument. That's why it has to be sorted, and finds the corresponding indices for everything to fit into. Now, notably, just like we've constructed our ranges, interval index considers the left element of the range to be inclusive and the right element to be exclusive. So essentially what we've done here is we've constructed a matrix where for each of the indices, we're slotting it into the range, and it's 0 if it's outside the left of the range, it's 1 if it's within the range, and then it's 2 if it's outside the range, right? And we want only the elements in this matrix that are within the ranges that we've specified. So we'll do 1 equals here to turn everything else into zeros. And we can assign this to M for matrix. Okay. So we start with one of each card. So we can get a vector of ones equal to length C by just doing C equals C here. And then we're going to do some matrix multiplication. Well, vector matrix multiplication, but same idea. So the idea is we're going to keep a vector of that basically counts how many of each card that we have. And then we're going to do a matrix multiplication against M here, which is, you can kind of think of it like our graph or something like that. So when we're doing vector matrix multiplication, we're going to take the vector, and for each element of the vector, we're going to multiply against each row, right? So as we get more and more copies of cards, those are going to get multiplied into our matrix here. And then we're going to add all of the rows together to give us the total numbers of cards that were generated. So we can do M plus dot times, and now let's do this like this. So we have the vector on the left. So let's think about this. So having a 0 in the first position makes sense because there's nothing in that column. And we took 1 times the first row, so we're generating 4 cards here. We're generating 2 cards on the second row. We're generating 3 cards on the third row, et cetera, et cetera. And this is a single iteration. And what we want to do is make sure that we are keeping the cards that we start with. So we can do like this. This basically just wraps the vector around both ends of the train, and we are adding our initial vector of just ones to the output of our matrix multiplication here. So we increment everything by 1, and now we can continue iterating. So we can use the power operator, and let's say that we run it 2 times, or how about 3 times, or 10 times, how about 11? Well, you get the same result, and I do this trick a lot in my videos, but you can probably guess that we can basically just do a power match here. So we basically run the function until it converges. And then all we have to do is add everything up to get 30, which is our answer for part 2 for the test input anyway. Okay, so hopefully you've kind of followed things to this point. Basically, the idea, just to sum everything up, is we're generating a matrix. So like if we look at M and if we look at C, you can see in the first row here, there's 4 ones after the first element. So these are the cards that we are adding, copies of cards that we're adding from the first card. And then the second element of C is 2, and you can see that there's 2 ones here, again, after the second element, right? So we construct this matrix, and then starting with one of each cards, we do matrix multiplication to simulate generating new copies of cards, right? And then we add our original cards back to make sure that we never lose those. And then having done that, eventually that converges, and we're able to just add up all the counts of the cards. By the way, so like this vector, 1, 2, 4, 8, 14, 1, you can kind of you can check this against the test input. So for the first card, we have 1. For the second card, we have 2, and then 4, 8, 14, and 1. So maybe this vector looks familiar. Okay, so hopefully you followed me to this point because it's about to get kind of weird. I was talking on the APL Discord for a little bit after posting the solution, and Rock 1507, I think his name is, pointed out something very interesting. So, oh boy, math. Wow, here we go. I am by far not any sort of expert in linear algebra or anything like this, but this result is super interesting. So if you have an infinite series, which is essentially what we're simulating with our power match of sum of matrix exponentiations, this converges down to the identity matrix minus your input matrix, and then finding the inverse of that. Now, so this matches what we do, and we do have a matrix inverse function in APL. I've literally never used this in an advent of code problem. It's been my goal for my life goal to be able to use this thing, and I finally get the chance. Okay, so stick with me. So if we think about this as kind of our part 2 line, a different way that we could do it is we could find the identity matrix. We can do that by taking our indices and doing an outer product equals, like so. And then we can subtract M from it. Okay, so this matches the formula here. We're taking the identity matrix minus our input, and then we're going to find the inverse. And then we're able to just vectorize it and add everything together, and we get 30. So this is wild. I've been looking for an opportunity to use this, and I'm glad that it came up. Beyond the formula and the fact that it converges, don't ask me why this works. Okay, this is dark magic. Anywho, so when you put everything together, it kind of it looks like this, and we can run it on our actual inputs, 04.txt. It's pretty fast. So part 1 is 28,750, which is the answer. And part 2 is 102,12,704, which is the answer for part 2. So yeah, this is actually this is a pretty neat problem, I think. And I think the imperative solution, basically doing like nested for loops, is probably a lot easier to conceptually understand. But I'm really happy that there's kind of a good array-based way to do this. And I'm trying to think more and more in terms of constructing matrices and doing matrix multiplications and things like that, even for things like, graph algorithms, things of that nature. So this is a good problem to be able to exercise that. Hopefully I've done a reasonable job of explaining all of this, but if not, feel free to leave a comment and ask me questions. Otherwise, stay tuned. Thanks for watching.